Well, hello everyone, and welcome back to Prep 33. In this video, we're going to look at a one-sample t-test. So here's our one sample. And the difference again with t-test and z-test is that now we do not know the population standard deviation. So let's look at the problem. Many grocery stores and large retailers, such as Walmart and Kmart, have installed self-checkout systems so shoppers can scan their own items and cash out themselves. How do customers like this service and how often do they use it? Listed below is the number of customers using this service for a sample of 15 days at the Walmart in Athens, Ohio. Is it reasonable to conclude that the mean number of customers using the self-checkout system is more than 100 per day? Use a 0.05 significance level. So let's frame the problem. To frame the problem, we're looking at is more than 100 per day, so find the probability of a sample mean above the population mean, because it's more than. Case one-tailed right. The distribution here is going to be t, not z, because we don't have the population standard deviation. And because it's t, we're going to have to use t.dist to compute the probability. Our null hypothesis will be there's no significant difference in use of self-checkout compared to the population average of 100. And the alternative is that shoppers use significantly more self-checkout on average than the population average of 100. The n value is going to be count 15, which is not a very big sample. And that'll come into play later. Okay, so the population mu is 100, that's given in the problem. And the expected variability, we don't know that for the population. The sample mean is going to be the sample mean of these. And the mu of the sampling distribution of sample means by the central limit theorem is equal to the 100. All right, our expected variability for the population, we don't have it. We'll compute it for the sample and then we'll use it for both. So standard deviation s of the sample values, and then we'll have the population equal that same number. All right. And then finally, for the sampling distribution of the sample mean, actually before we get there, let's take a look at what we've got so far. So you have the population here, the sample here, and we're really after can these differences come from the same population. So let's get our last number so we get the sampling distribution on here as well. And that's going to be equal to s divided by the square root of n. So there's our sampling distribution. And as you can see, both the population mean and the sample mean are well within the sampling distribution, so it's unlikely that this is going to be a reject. But let's play it out. All right, because it's a t distribution, we need to know degrees of freedom. Which in this case, since it's one sample t, is going to be equal to n minus 1. X bar minus mu, we need the observed difference from mu. So that's x bar minus mu. And then we need our t-score, which is going to be the quotient of the observed difference divided here by the expected variability. So there's our t-score of 1.25. And then we calculate the probability of getting that t-score. So that's going to be t dot dist dot rt, because it's right tail. There's the 1.25, and there's the degrees of freedom. So 11.6%. And you can see it here. All right. Now, let's show the critical region to prove that that is outside the critical region. Therefore, it should not be a reject. So level of significance for alpha is 5%. And now you can see that we're definitely outside the critical region. But let's see how this number was calculated, the 1.76. And that's going to be equal to t dot inverse, because we're going the other way, of the probability, but because it's right tail, we want to do 1 minus probability, and then the degrees of freedom are the same ones up here. So there's the 1.76 as far as our t-score. All right, so the conclusion is that we failed to reject the null, and the reason is that the probability is greater than or equal to alpha, and our interpretation of that is that there's no difference in self-checkout than the population average. So we're not rejecting the null. If you're wrong, this would be what type of error? That would be a type 2 error. All right. Now, before we move on to the confidence interval, it's fun to play a little bit of what if. Okay, in other words, is the problem here sample size? I mentioned that 15 is really small. What if we change that? Right now, I'm going to change it, then change it back. But watch what happens. Let's say I double the sample size to 30. You can see here, even though all these values are wrong, you can see here that this now moved underneath into the critical region at probability of 4.41. So with the same mean, had we had a bigger sample size, we actually could have rejected the null hypothesis. So this should tell you something, that sample size is important. And I can take that to an extreme. If I put 100 in here, you can see then we'd really be confident rejecting the null. So the idea, why is that the case? And you can see that also moving out further out in the tail up here as well. The reason that happens is because the larger sample size, the more precise you are, and the more confident that you can be that if things don't line up, if the means don't line up, then there really is a difference. But I'm going to undo that a couple times because I want to get back to where we had everything right. All right, now let's look at the confidence interval. So if you reject the null, which we're not doing, you're claiming the sample comes from a different population. What's the mean of that population? So let's go ahead and get the X bar. And let's get the original mu. And let's get the lower bound. So that equals X bar minus the absolute value of the critical value here times the standard error. And then the upper bound is equal to X bar plus the absolute value, the critical value, and that is times the standard error. So what this is showing is that the confidence interval for the mean is going to be between 98.9 and 106.43, but as you can see, our original mu fell within that confidence interval, which is why, it's another way of saying why we didn't reject it. All right, now let's see if we can understand relationships among variables like we did in the last exercise. So sample size n. As n decreases, the denominator decreases, so the standard error will increase. right? Which means we're less precise. It means we're not going to be able to conclude much. As this whole thing increases, then the t-score decreases or moves towards the center, which means that your probability increases and your likelihood of rejection decreases. All right, here if we increase n, the denominator becomes bigger, so the whole thing gets smaller, so that decreases. If this whole thing gets smaller, then the t-score increases or moves towards the tails. And then the probability in the tails is going to decrease, which means that we're more likely to reject. And we can do the same thing all over again, but this time for S. S is in the numerator, whereas N was in the denominator, so you sort of expect these to be opposite. So as S increases, numerator increases, we'd expect the standard error to increase. If that whole term increases, then we can expect the t-score to decrease or move towards the center, which means the probability increases, likelihood of rejection decreases. And here you've got the, if S decreases, then this whole fraction gets smaller, so this decreases. That decreases, then the t-score, because that's the denominator, the t-score gets bigger or moves towards the tails, which means that the probability decreases in the tails, which means the likelihood of rejection increases. So we have a nice causal chain, and what this one showed you is that if you have a small sample size, it's pretty hard to reject the null hypothesis if you increase the sample size with the same value of mu. Of course, it could change, based on the sample values. Then you have a greater possibility of rejecting. We'll see you next video.